Hi, as she said, I'm Rebecca Larson. I am a PhD student at the University of Texas at Austin. I will be graduating this year, so I'm going to have to learn how to not say that every time. But I'm going to be talking about a program that I've been leading on Keck called the Islands of Reionization. With my collaborators here listed below, I've highlighted Taylor Hutchison, who has a poster here at the Keck Science meeting. So please go check that out in the Slack channel when you have a moment. We had a great talk earlier yesterday from Patty about reionization, so I don't have to do a big overview. But reionization is the period in the universe's history about 13 billion years ago-ish or so, where all of the stuff in between galaxies went from being neutral hydrogen to ionized hydrogen. And that's the part of what we want to study because we don't understand that process, how it happened, what made it happen, what was the source of the ionizing photons, and all those kinds of things. And so we're targeting this time period in the universe's history, and we're trying to study it using Lyman alpha emission. And the problem with using Lyman alpha emission in the heart of reionization is that Lyman alpha photons are actually eaten up by neutral hydrogen. And so if you are in a galaxy surrounded by neutral hydrogen, because a lot of the IGM or intergalactic medium is neutral at this point in our universe's history, you're not actually going to see any of your Lyman alpha. It's not going to get to you. And so what we wanted to do was try to study this period using the most difficult way possible. So there's several different theories about how reionization happened, what were the sources of these ionizing photons, how long it took. And one of those is that you need big galaxies to emit a lot of ionizing photons, and it takes time to build big galaxies. So the reionization process here is going to start a little bit later, but then it's going to happen a lot quicker because you're going to have galaxies ionizing a lot more of the universe around them. And that's this gray line here. And so time is actually increasing from right to left. So where our redshifts are increasing from left to right. And so as time progresses in this gray line, you're looking at the ionized volume fraction of the universe. So how much of the universe is actually ionized? And this gray curve shows that it kind of takes a little bit to start up, but then it ramps up really quickly, where our observational evidence are those green points there at the top from quasar absorption spectra. Another theory is that, galaxies have escape fractions. So their ionizing photons can escape to some amount, depending on a lot of different things. And we're learning more about that in the local universe right now. But if we assume that it's halo mass dependent, so lower halo masses means a higher escape fraction, there's less of the galaxy to get in the way when these ionizing photons are trying to escape from them, then our lower mass galaxies have higher escape fractions and they can start this ionization process earlier. And so you don't need as much time to build a smaller galaxy. So even these smaller galaxies can start this reionization process earlier. And that's this blue curve here from Finkelstein in 2019, just showing that as time progresses, it doesn't have to be so dramatic. You can actually start reionizing the universe earlier. But the point in which these two things are the most discrepant is at redshift 9. Because in one scenario, you'll only have about 10 to 20% of the universe ionized. So you are not likely to see Lyman alpha emission because you aren't going to be in an ionized portion of the universe such that Lyman alpha can travel to you to be detected. Or in another scenario, you have like 60 to 70% of the universe is ionized and you're more likely to see it. And so what we decided to do was, again, like I said, the hard thing, and look for Lyman alpha emission from galaxies at redshift 9 using Keck. And that's what we did. So we had some galaxies that we were targeting photometrically determined to be at this redshift from our candles data. And we have 8 nights that I PI'd and 4 nights that Taylor PI'd. We use the J band because that gives you Lyman alpha at redshift 8.5 to 10.1. But there's not that many galaxies that we know of that are at this redshift, even photometrically. And so we had to fill all of our slits with some other science. And so that's where Taylor comes in. We actually can study carbon-3 and carbon-4 in galaxies at redshift 5 to 7, where we have spectroscopic redshifts from Lyman alpha, and ones where we don't. And so we can actually not just find the galaxies, but we can actually characterize them. And so take a look at her poster for a lot more information on some of the cool science that we were able to do in tandem with this redshift 9 search for galaxies. Okay, so we have Mossfire time, and I'm sure a lot of you are familiar with how this instrument works, but I don't know if all of you have tried to observe for 9 hours on one object, because it turns out there are some eccentricities with this instrument, One of them being that your objects will drift in the slit throughout the night if you continue to target in one place, even if you realign. And so what we noticed is we were having this issue where on the bottom we're showing over time in hours, the offset in both arc seconds and in pixels of a star we put on a slit so that we could track this phenomenon since we knew it existed. This has been found a couple times. MOSDEF is aware of this, so they do this in their pipeline. But we had to figure out a way to measure and correct for this. And so instead of just running our entire night of data through the pipeline and stacking it all together, we actually ran them in pairs. Each of our dithers were run to the pipeline. And then we had to shift them all and stack them ourselves by tracking this drift with the star that we put in the slit. So we've already now encountered a problem. We encountered another problem, which was that our objects are offset from where the pipeline thought they were going to be. And there is no discernible pattern to this. We do not know what that was caused by or why it was happening. Maybe bad, astrometry, unknown. But what we were finding is that our objects were expected to be at a certain pixel row in our slit, but we couldn't find out a pattern to the offset, and our galaxies needed to be stacked over multiple nights. But I needed to see my galaxies to stack them. I needed to stack them to see them. So I didn't know where they were. And there was a problem with this. And so it became more complicated very quickly. We had stars in our slits, like I said. We also had continuum sources from collaborators. And so we found that none of our objects were offset more than 3 pixels from the expected position. And here I'm just showing a low redshift galaxy that we had on the slits just to fill spaces. And you can see that this black line in the center here is where the pipeline expected it to be. And the bottom is actually the center of our object. Now this is great because I can see it. I can just say, oh, extract it right here. But again, I cannot see my galaxies in one night of data. I have to stack multiple ones. We're also using this different kind of extraction profile when we're extracting from 2D to 1D, where we use both of the negative traces from our dithers in our extraction profile. So we're boosting the signal of real detections and not getting too many noise. We're not boosting noise if there's just bright pixels here in the middle. And you can ask me more questions about that later, but that's basically all of the things that we added to the data reduction pipeline to kind of get as many photons as possible from these very faint galaxies. And so you can see when we line it up better, we actually get the full flux of our emission line. And that's what I really, really need, is as much flux as I can get. And so I am happy to announce we found one galaxy. Yes, applause, thank you. This was 3 years. And okay, so we found one galaxy. We found Lyman alpha in this galaxy at redshift 8.7. I'm showing here a 1D spectrum that is stacked from the 2 nights that we observed, plus the individual nights. I'm showing you the slits, plus the 2D spectra, and I guess the window is actually blocking our photometry from Hubble, but I promise it is there. So this galaxy is really interesting, not just because we detected Lyman alpha, we have a spectroscopic redshift, yay. But it's also physically very close to another galaxy at redshift 8.7 that was found by Ionization et al. In 2015. And if you do some cosmology, they're 3.6 megaparsecs from each other. And so this is interesting because in the EGS field, we also have photometric redshifts for 3 other galaxies that are at this same redshift 8.7 expected, right? So I'm showing those PFZs up there at the top. And this is interesting because we're thinking that this is an indication of an overdensity at redshift 8.7 in the EGS field. Because if you do an estimate of how many galaxies you would expect to find at that redshift in a field that size, it is 1, and we find 5. So what does that mean? That means that's very exciting. Hey, we found a really cool spot in the sky. This would be probably the highest redshift overdensity that we've detected. We have 2 galaxies right now, so we are hoping to follow it up with JDRST data, because this is also where our ERS data is being pointed. But what does this mean for reionization? We set it out on this journey to try to discover how reionization happened, which one of these was the proper answer. And so could these galaxies have made an ionized bubble big enough around them for us to have seen this Lyman alpha from them? And the answer is not so much. So, okay, so if you're looking here at this curve, I believe it's kind of blocked from the bottom, but this is escape fraction on the x-axis, and this is the radius of your bubble of ionized universe around this galaxy. Now, in order for us to see Lyman alpha, we expect that you need to have a bubble at least a megaparsec big, so that's this horizontal line at the top. So we need all of these curves to cross that line at a reasonable time. And so for our individual galaxies here at the bottom of the green and the blue, these are the two galaxies we've detected. So even if 100% of their ionizing radiation escaped the galaxy, we still would only make a bubble that's 0.6 megaparsecs. So we still wouldn't be seeing Lyman alpha from this galaxy, but we are. So why? So then we also know that we have more than just one galaxy. There's, expected number of fainter galaxies that we just can't detect right now with Hubble. And so if we do a luminosity function and add up all of those faint galaxies we expect to be at this redshift, then we get this maroon curve here. And if 100% of all of the ionizing radiation from all of those galaxies escape, we still aren't making a bubble big enough. Okay, but what if there's an overdensity as we're seeing? And so if we assume that this area of the universe is 5 times overdense and add that overdensity factor to our luminosity function, we actually create this dashed curve here, which at 20% escape fraction makes a ionized bubble big enough that we'd be seeing Lyman alpha from these galaxies. So that's even more evidence that there's an overdensity here. We also could be wrong about ionizing photon production efficiency and all of those kinds of things. And so assuming other things could also be a way that we would make a big enough bubble. And that's that dotted curve there. Both of these things will be tested with JWST. We can see those fainter galaxies, and we can also measure some of the nebular emission lines to get the proper ionizing production rates. So just in summary, we found Lyman alpha at one galaxy at redshift 9. We already knew of another one at the same redshift. Of our 8 nights plus 4 nights, a lot of time on Keck, we targeted all these galaxies and we only found these. It's consistent with overdense areas of the universe ionizing first, because there are more galaxies there to ionize the universe around them. And so potentially we're seeing this detection because we found this overdense pocket. And I can't exactly answer the question I set out to. We didn't find Lyman alpha in all of these situations, which would have been much more likely had we had 60% of the universe ionized versus 10%. So in order to put kind of these things in context, we'll have some data from JWST, we'll get more redshifts and that'll be great, but the survey size will be small. So we're actually probably going to need like GMT and Roman Space Telescope surveys to kind of get enough area coverage to answer the question we set out to answer. But do not fret. Keck did amazing. It is the most information we could have possibly squeezed out of this telescope, and I'm excited to report that we were able to detect something really exciting. So thank you, and I'll take questions. Questions from in-person folks.
So went for 12. You got 2. Were any of them not really rich H nitrogen galaxies? What I mean by that is, how many times did HST with the
So the question is, how many of our target sample maybe are not actually redshift 9 and are low redshift interlopers that are in our sample by accident? That's a great question. Steve's paper that came out, Steve Finkelstein's paper in I don't know what year it is, 2020, is talking about our sample. And we were very, very, very picky about these 12 galaxies that we looked at. In fact, we've kicked out 3 more. So I think we ended up with only 9. I looked at a lot more of our sample, and it turns out some of those are low redshift things. So the full end number is very small, but we were very conservative. So I would be surprised if any of the galaxies that are left, these 9 galaxies, are low redshift, because we've been very, very conservative in our sample selection. That being said, that will all be in our JWST data. The question is, how did I get my overdensity measurement? Is that what you're saying? We counted. So this project was never meant to be this results, to be honest. And so we could have done some measurements with theorists about like how often do we expect this situation to happen, and that is like a follow-up project that we're going to do. It's something we haven't really looked at, but we legitimately just counted the galaxies. And then in Ryan Ensley's paper, they did a measurement because they found three galaxies, a redshift like 7. And so we used that same calculation that they used to calculate the bubble size. And then we just did some back of the envelope calculations. It's not a super robust thing, but it was just a way to kind of argue why would we see Lyman alpha to begin with from this galaxy. Yeah. Yeah, so the question was, is there going to be more description in my paper about how we added all these extra steps to the data reduction process? And yes, my paper is currently 20 pages, and I think 12 of them are about my data reduction process and less about the science. Our flux calibration is a whole other thing that we did, and I could, if you have questions specifically about it, I could talk about that too, because we had to fix what we did when we did this. But yes, I do try very clearly to lay out the steps. I wish I wasn't an IDL person and I could share it, but but I did try to be as descriptive as possible. So if anyone else is encountering these issues or trying to do very, very, very faint objects with a lot of keck time, you could potentially improve your data this way. All right, well, that was really exciting. Let's thank Rebecca again.